But let's assume for a moment that you are dealing with visible range of the frequency. So what is the visible range that we observe, that we see? How many nanometers to what nanometers?
I think it was 700.
That's true. It's from... Yes, Ismiana, what did you say?
I think that it is from 650 to 700 nanometers.
That is true. Actually, it can go a little lower. The blue color that we see from the spectrum, from the rainbow, the blue is 400, the red is around 750. So the range that you provided, they are completely acceptable. But let's think for a moment something like 400 to 800. If it is something between 400 to 800 lambda over 4, that means something between 100 nanometer thick layer up to 200 nanometer thick layer, which is 0.2 micrometer. And the 0.2 micrometers, it's a distance which we can technically control without too much effort. It is difficult, of course, okay, but it's something we can, with our technology currently, we can do it for a small amount of money. Now, if we go to much smaller wavelengths, the prices change exponentially. So, for example, you can get a laser source, or a light source, which Besmir made a presentation before, in the order of 400 to 800. Then their respective mechanical designs, which would be such, in this case, a coating, or the mechanical designs where Dorian explained, where you had some resonating O-rings. So you have something which you have to do it yourself. It's not like the piece of glass which has where the molecules are oriented on a specific orientation, or they are completely random. It's not like that. The moment you need to draw something, you should know that we are good enough to make an optical resonator which is as big as 300 nanometer, which is 0.3 micrometer. We can do that. But if you go into length scales, which are like 4 nanometers, we cannot do it, okay? I mean, we cannot do a mechanical structure which can make, because always the length scale of the optical light, photon or laser, should be comparable to whatever we have mechanical systems that we want to measure, etc. Now, a laser source with a wavelength of 15 nanometer, I wrote it before a while in the comments section. If you have not read it, a laser at 15 nanometer, it costs 1 million euros. Okay, it is really expensive. But a laser source at optical, so if you buy a laser pointer to show something, PowerPoint slides during a presentation, you can buy it for 5 euros. So from 5 to 10 euros, from 10 to the power 1 price for a laser pointer, it goes from 10 to the power 1 to 10 to the power 6 euro for another laser wavelength at 15 nanometer. So I made a comment regarding all the presentations, but at least in your case, it looks like it is relevant for you, Christina, to probably report in your written document that the thickness of your optical coating is over 4, which makes it something from 100 to 200 nanometer. But please, I really want to take like a take-home message for everyone. Everything, whether it's an electromagnetic wave or a mechanical system or a biological system, which is 1 micrometer thick, or a hair. So you have a hair, you pick up one, if you have, and it is 40 micrometer or 10 micrometer. So these length scales of mechanical systems that you want to measure or to interact with should be comparable to the wavelength of the wave that you are using for observation. You can continue, Christina.
Okay, so we can continue with the optical filters and go very quickly through this, because we've provided also a few pictures in the PowerPoint. We can see that the filters are used to select the range of wavelengths that will be transmitted, or some of them that will be attenuated. There are two main large categories, which are absorptive filters and dichroic, and they differ in the way they treat the unwanted wavelengths. For example, the absorptive filter will block the unwanted wavelengths inside the filter, so to be contained inside the filter, and they will not be reflected. While for the dichroic filters, all the unwanted wavelengths will be, all the unwanted range will be reflected, and all the other part that we want will be transmitted.
Okay, and can allow me to make another comment. It is relevant to what you said right now, Christina, that you are mentioning right now a complete reflection and zero transmittance for a very narrow bandwidth of a light. This is a notch filter. Okay. So
Yes, we've also, sorry to interrupt, but we've also mentioned them in the PowerPoint.
okay.
There are a few pictures which are very good and very easy to understand and to even for us to explain to you.
Okay, now why I mentioned notch filter, because in the previous slide, the Dorian showed us some prices of notch filters at around 477 nanometers, which was huge in size, which was much bigger than I would expect for 300 euros. But they mentioned the keyword of notch filters. So those are filters which completely filter out in the continuous spectrum of whatever initial light, incoming light you have. You create a dark spot right there. So that is a notch filter. Okay, you can continue again.
Then we have given a brief explanation to optical windows, which are considered as flat optically transparent plates that maximize the transmission of a wavelength while minimizing the reflection and absorption. They are designed to protect an optical system from dust, debris, and environmental conditions such as temperature and pressure changes. And while deciding which optical window is appropriate for any application, we should keep in mind the material properties, and in this case are included the transmission, the refractive index, the density, and the thermal expansion coefficient. For example, for the last one, the thermal expansion coefficient changes the size of the glass depending on the changes of the temperature or the density that determine the weight of the optical assembly of the glass, for example, based on the change of the temperature. And then we have divided optical windows into two categories, which are parallel and wedged one. Parallel maximize the transmission, and wedge direct the transmitted light at a specific angle. This angle actually can be calculated. Here we have to do with optical wedge, or that is a lack of parallelism between surfaces, and the wedged angle that I mentioned before is related with angle of deflection by the formula that angle of deflection is n-1 times wedged angle. We have also a data sheet that shows some specification about the optical coatings constituted to the optical wedge.
Okay, so we can go in the PowerPoint now. In presentation, we mentioned before about the single wavelength AR coatings, and they are called V coatings because of the shape of the curve or the shape of the graph. And we can say that V coatings are used to increase the transmission over a very narrow wave band, which is centered at a specified wavelength, which parameter is called design wavelength. Here we can see some data from I think it's from Edmond Optics, where we have different design wavelengths in nanometers, for example, 266, 343, and we see that for all of them, the reflection or the reflectance in percentage would be something less than 0.25%. The third column is very important, and we'll see this parameter usually in data sheets. It's the damage threshold. We know this as LIDT, or laser-induced damage threshold, and it's a parameter that indicates the highest quantity of laser radiation incident upon an optical component for which the probability of damage is 0. Here we also have another graph, it's about a broadband AR coating, which it covers a wider range of wavelengths for which the reflectance will reach a minimum. And in the next slide, this is a bandpass filter, and two important parameters to define, because also these are present always in datasheets, are the full width half maximum and the central wavelength. And if we give a definition, the full width half maximum is the spectral bandwidth over which a filter transmits, and the lower and the upper limit can be, let's say, are defined at the wavelengths for which the transmission is half the value of the maximum transmission. In this case, it's 50 because the maximum transmission is 100, but it may be less. It depends.
Yes.
And also the central wavelength, it is the midpoint. Traditionally, the peak transmittance will be a point very near the central wavelength.
In this slide, we have shown the data, the optical filters that we mentored in the report. The first one is a bandpass filter. The second is a notch filter. Then we have a short pass and long pass. The bandpass filter block or transmit a range of wavelengths while blocking the other part. Notch filters block this part of wavelength and transmit the other one. About short pass and long pass, here we have to do with the cutoff frequency or wavelength, and in the short pass filters, for every wavelength or frequency below the cutoff are transmitted, and to the long pass, every wavelength and frequency over the cutoff is transmitted.
So here we have some notch filters, and this data is taken by Edmund Optics, and we also have the prices, which they are not too large. They range from 245 to 445, and we have the central wavelength that we mentioned before, and full width half maximum, also the transmission range.
How much is the full width at half maximum?
Okay, for
20, 30?
Or the first one, which has a central wavelength 355, the full width of maximum in nanometers it's 17.8, but we can see that it increases, and maximum values for this company, for products of this company, is 53.2.
Okay, 53, but for a wavelength of 1000 something, 1064.
1064.
Okay.
And price is the same. I mean, for this product, it's the same, $245.
Yes. Okay.
In another slide, we have a long pass filter, which Ismail mentioned before. In long pass and short pass filters, we always have a cutoff frequency or a cut-on frequency. In this case, we consider the wavelength, in fact, which is 600 nanometers for this case, and the tolerance is plus minus 5 nanometers. The transmittance range is it varies from 610 to 1020, 200. I'm sorry. The transmission is something above 80%. I think the price of it is $120.
Okay.
We also have a temperature range, which is from minus 50 degrees Celsius to plus 100 degrees Celsius. In this case, it's a bandpass filter. I think it's the opposite of a notch filter. And we see that the central wavelength is 330 plus minus a tolerance, which is 6 nanometers, and also the full width of maximum, which is 95 nanometers. This data is provided by Aluxa, which is a company that produces products about optics, and not only bandpass filters, but also lenses and contacts and other things. But the price for this specific product, which has those products have titles, and is $205.
Aluxa, never heard about this one. Strange. Okay.
Yes, I mean the most part of this material was taken by Thor Labs, by Edmund Optics, and by another company which I can't remember the name right now. But this was a company that had some online catalogs.
Oh, I see it. I see it right now online. I'm checking this one. It looks like it's a good one, but I've never heard. Okay, that's good. Aluxa.
Okay, the next slide is about Thor Labs, which I think we've mentioned before.
Yes.
In this slide, we have chosen a datasheet from Thor Labs that consists of sapphire wedged window, which is uncoated. We can see some specification like wavelength range, which is 150 nanometer to 4.5 micrometer, and the substrate, which is sapphire. The prices as well that varies, but I can't see very well.
Okay, it's about two different models because they have different titles. And the first one has a price of $80, while the second one has a price of $110. And these are taken by Thor Labs. You also have some, the pictures here. And two other pictures are very interesting. Is about the parallel window on the wedge. And we said before the functionality of the wedge. And so what it does, it takes the transmitted wave and directs it to an angle. And we said that it can be measured. And this is called angle of deflection, namely delta.
Okay.
Formula was n-1 times the angle of the wedge. So that was our presentation.
Okay, that was good. Anyone has any question? Okay, so you talked here about notch filters being the complete opposite of the bandpass filters. That's how they are. So notch filter, it's a Gaussian function upside down, which is 0 at the center and 1 outside. Okay, so you can think about of a Gaussian distribution as a function of x and y. Okay, now thank you for the presentation. And now regarding the rest, we might push some of the presentation for tomorrow but I want to get your opinion.
Moraj
Yes.
emailin që më dërguat për ta shtyr prezantimin, se
Po.
dia që të vononim kaq shumë sot, nuk e di sa të mundur e keni, po unë nesër më duhet që në mëngjes të vi tek Epoka dhe nuk do kem mundësi që ta prezantoj projektin.
E kuptoj. Po nëse vjen te Epoka, merr dhe laptop me vete.
Nuk e marr dot se shumë i madh laptopi që kam unë, po posterin do ta sjell.
Posterin